Okay, I guess we can get started. Welcome everybody to our monthly C2QA Colloquium. It's a pleasure to have Nathalie de Leon as our speaker today. She, as you all know, I'm sure, is the leader of our materials thrust in the center. And she has done work on optical defects in diamond, and recently has come into the world of superconducting qubits. And she just mentioned to me before we started, she has a review article on materials for, I guess, quantum devices coming out in Science this week. So I commend to you. And so we look forward to hearing about your overview of materials for quantum. Thank you.
All right, thanks, Steve. I think when I agreed to this colloquium, I hadn't realized that I could get out of it by pointing out that I had done a Quantum Thursday talk. So sorry for the double header this year, but hopefully after this talk, you don't have to hear from me again for another 4 years or something like that in the center. Okay, so I guess the last time I talked to C2QA, I was mostly talking about color centers for quantum networks. So I thought I would talk about something different today. And my plan is to discuss some general efforts that we have in correlating materials analysis with qubit measurements to systematically eliminate sources of noise. So my group, broadly speaking, is interested in looking at atom-like systems in the solid state. For the last 20 or 30 years, for the last several decades, there's been a lot of work on trying to develop cold atoms as nice quantum systems because they have very long spin coherence times and efficient optical transitions that you can use to sort of manipulate these degrees of freedom. So what most of my group is focused on for the last several years is trying to realize these systems in the solid state where you can imagine integrating these atom-like systems into scalable devices. And this has a lot of different applications in quantum information processing, but also because you can couple well to photons, you can use these for quantum networks and also for nanoscale sensors because you now have a true solid state object where you can have these point sensors. So my group is working on technologies along all of these tasks. So we're using color centers for nanoscale sensing and surface spectroscopy. And I talked last time about our efforts to look for new solid state defects for long distance quantum networks. And then recently we've started a collaboration in a completely different material system with Andrew Hauk and Bob Kava to look for new material systems for quantum computing using superconducting qubits. So I'll just focus on 2 stories, time permitting today, on trying to deploy these color centers for nanoscale sensing, and then using some of the lessons that we learned along this path to try to understand how to improve material systems for quantum computing. So the system that I'll be talking about for the first half of my talk is the nitrogen vacancy center in diamond. This is a color center in diamond that consists of it's a substitutional defect where you take 2 carbon atoms out of the lattice and then you put in 1 nitrogen atom and you leave behind a vacancy. So you have an NV center. And this gives you very deep electronic levels that are basically mid-gap. So if you look at the valence and conduction band edges of diamond, the NV ground state is somewhere halfway between these 2 edges. And you even have enough room to have an excited state all inside the band gap. So because you're very far away energetically from these band edges, to first order, you can think about this as just localized molecular orbitals where you don't have to consider the extended lattice in describing this defect. The NV center is sort of special because you can have very long spin coherence times even at room temperature. It's a ground state spin 1. And it turns out that there's a convenient method for optically manipulating and measuring the spin, even using off-resonant excitation. So if I just take essentially a green laser pointer and point it at an NV center, if I start out in one of the spin sublevels, I get some fluorescence rate. And if I start in one of the other spin sublevels, I have a spin-dependent intersystem crossing to a dark state, so it decreases the total fluorescence. So just by counting the number of photons I get per second, I can read out which spin state I'm in. So a lot of people are interested in using the NV Center for tasks like magnetometry, because you can now read out this spin resonance transition using optical microscopy. And then you can look at, for example, the splitting between these two different spin transitions to read out the local magnetic field. And there have been a lot of demonstrations of sort of basic quantum information processing tasks using NV centers, because you can coherently manipulate and measure the spin. Because of these properties, there are now dozens of groups around the world who are all focused on this one color center in diamond. For nanoscale sensing, the properties that we care about the most are that you have these very long spin coherence times, which allows you to get very, very sensitive measurements of the local magnetic field. And of course, this off-resonant optical readout and initialization is really important for room temperature and sort of ambient condition sensing. And importantly, if you combine all of these characteristics with the fact that we can do single center imaging using microscopy techniques that have been developed over the last 30 or 40 years, you can take advantage of the fact that the NV center, interacts with its environment with extremely strong gradients. So if you plot, for example, dipolar coupling, you get these contours of equal dipolar coupling that are basically separated by angstrom scales, and use this as a point sensor. So in some sense, you can sort of think of this as a magnetic resonance imaging tool with the largest possible magnetic field gradient. With this property in mind, there have been a large number of groups who have been focused on trying to use the NV Center for nanoscale sensing, for example, by placing biomolecules at the surface of diamond and using the NV Center to do nanoscale nuclear magnetic resonance. People have recently sort of pushed these techniques to achieve even chemical shift resolution of nanoscale volumes in NMR. And there's also a large number of groups that have been working on trying to deploy NV centers to look at condensed matter systems. This is a beautiful example from Patrick Malatinsky's group, where they used a scanning NV magnetometer to look at magnetic domains in chromium triiodide, and we're able to see something that you just couldn't really access with other techniques. Pushing this to the limit, you can even use NV centers, as I mentioned earlier, to do things like magnetic resonance imaging at the single atom scale. And this is some beautiful work from Tim Tamaniau's group at Delft from a couple years ago, where they used an NV center to couple to local carbon-13 nuclei in the bulk diamond, and then applied various pulse sequences to tease out where exactly these carbon-13 nuclei are. And here they mapped out the positions with sub-angstrom resolution of 27 carbon-13 nuclei in the vicinity of this NV center. So it's pretty clear that if you could really deploy this as a sensor in various tasks, that this could be quite powerful, because you now have the ability to do this magnetic resonance imaging at single molecule and even single atom scales. Okay, so the goal is to try to bring this NV center close to some sensing target, because both your sensitivity and your resolution really require close proximity to the sensing target. But one problem that we run into immediately is that in order to bring the NV center very close to the sensing target, you also have to come close to this diamond surface. And while you can get this, sort of beautiful long coherence time in the bulk and do these very nice experiments, what we see is that the quantum properties of the NV center really degrade as we come close to the surface, because you start to see a lot of noise that arises from uncontrolled states at the surface. And one of the ways that we know this is that you can just look at individual NV centers. Each of these colors is a different sample, and each of these points is a single NV center, and look at their Hahn echo coherence time as a function of their depth away from the surface, and we see something that looks like power law scaling. So while the coherence time in the bulk is something like milliseconds, just limited by your spin lattice relaxation time of a few milliseconds, you can see that by the time we get to within, say, 10 nanometers or 5 nanometers of the surface, we have sub-microsecond coherence times. Okay, so what we'd like to do is try to improve this scaling so that you can actually use the NV center as a nanoscale sensor. And the challenge here is that the NV center is really a very sensitive probe, but it's very non-selective. All that it tells you is, I have a long coherence time or I have a short coherence time. So what we wanted to do was try to understand the surface noise by looking at the material directly. And there are a number of surface sensitive techniques. They're all challenging in their own ways, but maybe more fundamentally, they probe much larger areas with fairly low sensitivity. So a priori, it's not obvious that your surface sensitive technique is going to give you information that is useful from the point of view of improving NV centers. And in addition to that, there's a number of sort of technical problems working with diamond specifically. So what my group worked on was a broad project of trying to develop techniques to study the diamond surface in detail by correlating many of these spectroscopy tools with the kind of nanoscale spectroscopy you can do from the point of view of the NV center. And our initial shot at this was really a fairly scattershot. So we just tried to get beamline time and user facility time everywhere that we could and tried a very large number of techniques to study the diamond surface. Everything in gray here is things that we tried that did not give us information that correlated with NV properties. And we sort of landed on a handful of photoelectron spectroscopy tools that actually did seem to correlate well with what we could see from the point of view of the NV center. And then we can do something a little bit more sophisticated with the NV center than just ask it whether or not it has a long coherence time, a short coherence time, which is to drive it with different pulse sequences that are sensitive to different components of the noise to try to study the local noise path in detail. So just to give you a small flavor of the kinds of things that we figured out in this project, one thing that we sort of immediately realized was that many people in the community were using oxygen terminated surfaces to stabilize the NV charge state, but that different oxygen terminated surfaces can be very, very different from each other, even with the same nominal processing. And in particular for diamond, one of the big challenges is that processing is very hysteretic because it has you have very anisotropic etch rates for most processes. So for example, if you start with two different surfaces that have very slightly different surface roughness, and you put them through exactly the same processing like oxygen annealing, you can end up with very, very drastic changes in surface morphology for the final surface. So these are just AFM scans that show that you can get a lot of runaway surface roughness. And what we could see using, for example, near-edge X-ray absorption fine structure spectroscopy, where you're basically using X-ray absorption to probe the density of unoccupied states, we could see a huge difference in just the electronic structure between these two surfaces with different morphology. So here, everything above about 289 EV is the band structure of diamond. This is just the conduction band, but everything that's lower than that is just a defect state. It's not supposed to be there. And you can see that this rough surface has a much, much higher density of unoccupied states near the conduction band edge. And these are sort of natural candidates for these electronic traps that might lead to magnetic and electric field noise. So using these kinds of spectroscopy techniques as a feedback tool, what we were able to do is develop a long kind of multi-step process to create pristine surfaces to try to get better NV centers. So we start with sort of state-of-the-art polished substrates. That leaves behind a lot of polishing damage, which we have to use reactive ion etching to remove. We discovered that there was quite a bit of residual etch damage from that RIE step. So we had to have a second RIE step to remove some of that etch damage, which again leaves behind a little bit of damage, which we have to thermally anneal away. So we sort of intentionally graphitize the diamond and then clean off that graphitic carbon. And then finally, we end up with a surface that is relatively disordered, so we can do a final oxygen annealing step to get a nice chemical termination. And what we're now able to do, as long as you are very careful about the surface morphology and contamination at every single step, we're now able to achieve oxygen annealed surfaces that have typical RMS surface roughnesses of around 100 picometers. Okay, so using this processing, just to give you the punchline, we are able to get NV centers with coherence times that are extended by about an order of magnitude at the same depth. So these are all of the data points that I showed you earlier. And now these dark points are from one of these surfaces that that's gone through our full processing. Okay, so if you're not interested in surface spectroscopy, you can kind of just take a nap for the next 5 minutes or so. And what I want to do is sort of go into detail in understanding what exactly led to this improvement. Okay, so there are a lot of steps to unpack here, but what I will focus on is just sort of the impact of this very, very last step. So if we compare NV centers under this surfaces after we've done high temperature annealing versus this surface after we do our final oxygen anneal, we can learn something about how these different chemical states actually contribute to noise at the NV center. So we can look at an individual NV center before and after this last oxygen annealing step, and we see that the Hahn-Echo coherence time is extended by over a factor of 2. And then we can also do dynamical decoupling to probe this noise bath across a very large frequency range. Basically, as you add more and more pulses, you probe higher frequency components of the noise bath. And what we find is that after oxygen annealing, you have this improvement in T2, and you have this improved T2 across a very, very large range of pulses. And maybe importantly for within our community, you can see that before this oxygen annealing step, you hit a point where you stop winning from increasing pulses, indicating that you really have a high frequency noise bath that you can't decouple from. Whereas in our oxygen annealed surfaces, you see that we just have this full kind of linear scaling that you would expect. Okay. In addition to dynamical decoupling, we can take advantage of the fact that the NV center is a spin 1 defect to look at different relaxation processes to learn a little bit about the noise. So for example, magnetic noise will only drive single quantum transitions from ms equals 0 to -1 or 0 to +1. But if you look instead at relaxation that changes the angular momentum by 2, so between ms equals -1 and ms equals +1, magnetic noise cannot drive these transitions. So these should give you a picture of how much electric field noise you have. And what we see is that this last oxygen annealing step gives you a very large change in the single quantum T1, but a very small change in the double quantum T1. So we can say that the change in noise is predominantly magnetic. And we can put sort of all of these different measurements together because they all are at different frequencies and try to plot the relative contributions. And we see that we do indeed have a very broadband noise bath and that it is predominantly magnetic. Okay, so that's what we can learn from the point of view of the NV centers. And now we can look at X-ray spectroscopy to do direct characterization of the surfaces to see what that looks like. And maybe somewhat to my surprise, when we looked at, for example, again, NextSAFs at the oxygen edge to try to learn about these oxygen groups at the surface, these two surfaces gave qualitatively similar oxygen K-edge spectra. I'm sure that there are some photoelectron spectroscopists in this audience that would cringe at my characterization and they can see very subtle differences. But my characterization would be that there's a sharp peak here and then kind of a broad shoulder. So we are generally not looking at drastically different chemical states. However, if you just look at the angle dependence of this NextSAF spectra, you can see that before oxygen annealing, you get almost no angle dependence, whereas after oxygen annealing, we have a dramatic angle dependence. And what this indicates is that the surface starts out with a high degree of disorder, so it washes out any angle dependence that you might be able to see, whereas after this oxygen annealing, we have something that's atomically ordered. At the single monolayer of atoms at the surface level, and then you recover this nice polarization dependence. In addition to that, it turns out that this degree of order and disorder has dramatic consequences for the electronic structure. And what we find is that if we do ultraviolet photoelectron spectroscopy, we can read off the electron affinity at the surface. And after this oxygen annealing step, the electron affinity changes by, almost 1.5 electron volts, which is the highest positive electron affinity that's ever been measured for an oxygen terminated diamond surface, and sort of solves a long-standing question in the field, which was that if you calculated the electron affinity for hydrogen terminated surfaces and then just measured it, you basically got the right number. Whereas for oxygen terminated surfaces, people sort of systematically saw a much, much lower electron affinity than you expected. So what we found is that this disorder suppresses the electron affinity and really changes, the electronic structure of the surface dramatically. Okay, so just to show you that we have really good control over these surfaces, what we can now do is sort of look at a single NV center under this high temperature annealed step, and then look at its T2 change after this oxygen annealing. And then we can reset the surface by doing another thermal annealing step, and we find that the T2 goes back down. And we can do a final oxygen annealing step and sort of recover the T2. And what we find is that this pattern is reproducible across all of the individual NV centers that we measure. So just to give you a short summary of the first part of the talk, what we've been able to show is that if you use complementary spectroscopy techniques to discover sources of noise, we're able to achieve a new oxygen surface termination for diamond that allows for highly coherent shallow NV centers. And we're now able to get NV centers within 5 nanometers of the surface with dynamically decoupled coherence times exceeding 100 microseconds. Okay, so the other story that I wanted to tell you about was a little bit of more detailed characterization, looking at different kinds of measurements that you can do using the NV center. So far, everything that I described is sort of, very straightforward. We basically just did dynamical decoupling to probe the spectrum of the noise path that the NV center was looking at. So now what I'd like to tell you about is a short story about how you can look at these decoherence curves in much more detail to learn a little bit about the bath that you're looking at. So what we're aimed at here are trying to understand some of the spins that you can see spectroscopically at the surface of diamond. And our main tool is to do double electron-electron resonance measurements. So the idea is that you do a Hahn echo sequence on the NV center, which cancels out your quasi-static noise. And then in the middle of this Hahn echo sequence, you apply a frequency selective pi pulse to this surface spin bath. So what you should do is cancel out all of the noise except for these surface spins, and then you can use this to look at the degree to which you're coupled to surface spins. So this is an example of one of these measurements. You start with some Hahn echo coherence curve here in blue, and then if we apply this selective pi pulse to the surface spins, you can see that we suppress the coherence. And then if we divide these curves by each other, then we get out a signal that corresponds to the free induction decay due to these surface spins. Okay, so if we do a lot of these measurements across different NV centers and look at that as a function of depth, then here what you can see is that in general, this coupling to Deer spins increases with decreasing depth. And this is a number of surfaces that were all prepared in the same way. And then these are surfaces where we were trying to decrease the Deer spin density. And you can see that indeed we get a lot of points that are below sort of this band in terms of gamma Deer versus the NV depth. So then we set out to try to understand, where these surface spins come from and to try to control their density. And what we found is that looking again in carbon edge NextAFs, if you zoom in on this little range here, then you can see that all of these samples sort of before oxygen annealing show this little peak at 282.5 EV that corresponds to dangling bonds at the surface, whereas our oxygen annealed samples do not. And we see that this correlates with this Deer contrast that we can see, this Deer coupling rate. Okay, but I just told you a whole story about how a lot of things change after you do this last oxygen annealing step. So what we needed was some way to selectively remove these Deer spins, these surface spins that didn't change very much about the rest of the electronic structure. So if we did in situ annealing to 650 degrees, then you can see that the oxygen edge doesn't change very much and the carbon edge doesn't change very much, except if you zoom in on this very, very little peak at 282.5 eV. At 650 degrees, the dangling bond peak goes away. So we're pretty confident that this is a selective annealing procedure. And then now if we do, again, Deer coupling measurements on individual NV centers in the same sample before and after the 650-degree vacuum annealing, we find that the Deer spin coupling rate goes down significantly for all of the NV centers. Okay. So we can selectively tune the surface spin density, but then we're immediately sort of confronted by a number of puzzles with this data. So the first is that if you just extract the density of surface spins using this data set here, which is the coupling rate versus depth, then what you extract is that the surface spin density corresponds to a linear spacing between surface spins of around 14 nanometers. And that is much larger than the distance from the NV centers to these surface spins. So it means that on average, your NV center is much closer to the surface spins than they are to each other. And in that regime, you shouldn't really see monotonically increasing Deer coupling rate as you go close to the surface. What we would expect to see instead is some increasing variance in the surface spin signal. Okay, so that was the first puzzle. The second puzzle is that if we tried to fit the shape of the decoherence very carefully, we found that we couldn't fit it well. So this this free induction decay really should look like a signal that looks like e to the minus gamma Deer t to the n, where this n should be 2 in the quasi-static limit. And you can see that if we try our best to fit this data to e to the minus gamma t squared, we get a very poor fit to the data. That's this orange curve here. And instead, what this looks like is something that is a more stretched exponential, so a smaller exponent. And what we found, if we now did this fitting, allowing this exponent to be a free fitting parameter across many, many data sets, so many NV centers and many samples, we found that very, very few of them fit to n equals 2. And in fact, there were even many NV centers that fit to n of less than 1. And we could see a general depth dependence where we saw lower exponents as you got to shallower depths. And this was especially surprising because you can write down fairly simple arguments for what the bounds on this exponent should be. And this predicts that the exponent has to be between 1 and 2 for well-behaved monotonically decreasing noise. So the fact that we could see many data sets where this n was less than 1 was very puzzling. Okay, the third piece of puzzling data was that, again, we're in a regime where the NV center should be closer to these surface spins than they are to each other. And in that regime, we should be able to see coherent coupling to single spins a lot of the time. But we would actually only see coherent coupling in a couple percent of NV centers across a data set of a few hundred. And intriguingly, we could even see this coherently coupled signal in the few NV centers where we could find it blink on and off in time. So if we, for example, just park at this evolution time to look for coherent coupling, then you can see that the magnitude of this signal kind of is bistable and shifts around on a time scale that's relevant to humans. Okay. So why might we see this stretched exponential decay? So there's one fairly simple explanation, which is that let's say I start with some high density bath, and that gives me some coherence decay that fits to n equals 2. And then if at some other time I sample a different density bath that gives me a longer coherence decay that also has n equals 2, then I have to average these things together, and I get something that now looks like this stretched exponent, where this n can be less than 1. One possible solution to this puzzle is that we're looking at some kind of configurational averaging where the NV center looks at different spatial positions of the surface spin bath at different times, and then we average them together. And sort of separately in my group, we had already been looking at things like the photoionization dynamics of color centers in diamond. And what we could see is that these photoionization events, which are basically 2-photon ionization of the NV center, can change dramatically as you change the properties of the surface. So we can kind of control this ionization rate by changing characteristics in terms of contamination and surface termination. So in general, we kind of know that these charges are moving around a lot. And here we are studying the dynamics of NV centers in detail, but it's also plausible that these surface spins are sort of changing and reconfiguring in time as we shine, a milliwatt of green laser light on this diamond. Okay, so now with this model that these spins are hopping around, we can now just do numerical simulations of what you expect in terms of the coherent signal at the NV center. And what we find is that, for particular configurations, you just have this, this cosine decay. But then as you average many of these things together, you end up with this the stretched exponent decay. And what we find is that indeed, for very shallow NV centers, you end up with a very small exponent. And for deep NV centers, you sort of recover this n equals 2. And then you have some transition range between them where you can get everything in between. And one of the things that we found was that for very shallow NV centers, the NV center effectively becomes part of a 2-dimensional bath, and this n actually goes to 2/3. Okay, so those are just numerical simulations. So we can also sort of write down an analytical model, which turns out to be difficult to arbitrarily integrate. So instead, we can kind of solve it at short times and long times. And what we find is that for sufficiently short free precession times, you do just recover this n equals 2 shape of your decoherence curve. But then for very, very long times, you get an exponent that looks like the dimensionality of the bath divided by the strength of the interaction. So in this case, it should go to 2/3. And in particular, what we actually expect to see is a critical crossover time. So this is now plotted on a log scale, which is not super easy to understand intuitively, but has the advantage that now the slope of the line just gives you the value of the exponent. So you can see that at short times here, you start at n equals 2, and at long times, you go to n equals 2/3, and you actually have a fairly sharp transition between these two ranges. And the position of this crossover time just depends on the depth of the NV center. So there's actually kind of a nice geometric interpretation of all of this, which is that at very, very short times, the NV center basically senses the distant contributions of many of these surface spins. And then given sufficiently long time, it has enough time to coherently couple to a few of the surface spins, and then effectively really looks like it's part of the 2D bath. So this critical crossover time is just determined by the depth away from the surface. So you have, this is now depicting time as this sort of dipolar coupling volume, and you have some time delay before this volume intersects the surface of the diamond. Okay, so we can now go back into the data and intentionally try to oversample it to look for evidence of this critical crossover time. And we indeed see that if we plot these coherence decay curves, again, on a log plot, that at short times, we have something that fits to n equals 2, and at long times, we do see this, this bend to n equals 2/3. And now if we extract this crossover time and use that to read off the depth, then we can compare that to measurements of the NV depth that we can get by proton NMR, and we see that we have very good agreement. So the numbers here are the proton NMR numbers, and then the radius of the volume sensed is now plotted up here. So everything that I described to you is actually quite generic for just disordered spin systems. And you should be able to see this in principle in, ensemble ESR and NMR experiments. But the key thing here is that the time at which this crossover happens is set by sort of the shortest distance between spins. So usually this timescale is inaccessible because it's very, very short. Here, because the NV center is a separable probe, you can set this the distance to your bath and therefore this timescale arbitrarily. So this allows this crossover time to be observed. Okay, so just to briefly summarize this section, I think what we showed here is that if you do very careful measurements of this decoherence and really pay attention to the shape of the coherence curve, you actually have a very powerful probe of a lot of parameters of the spin system that's of interest. And in particular, you can read the dimensionality and the dynamics of this spin system. And the ability to choose the distance is really key. So the fact that you have this nanoscale sensor where you can separate it from the bath that you're interrogating is really what enables these kinds of experiments. So there's a number of other kind of activities in my group that I'm not talking about today, all revolving around shallow NV centers. So we've been working on, I mentioned this briefly, but charge dynamics of shallow NV centers. And then we are also working on an ultra high vacuum microscope with a surface science and preparation chamber attached. I think the students are actually baking it out right now. And separately, we've also been working on trying to do surface functionalization of diamond to try to bring these targets very close to the NV center. Okay, so now what I wanted to do is just completely change gears. So what I've told you is a number of stories about how we've systematically improved NV centers and then used them as detailed probes of their surroundings. And a few years ago, I started talking with Andrew Hauk and Bob Kava about whether or not these kinds of approaches could be helpful for superconducting qubits. So in particular, if you just look at sort of the coherence time or lifetime of superconducting qubits over time, so this is like a Moore's law plot, there was really an impressive sort of trajectory of systematic improvements, mostly through device design, to try to avoid sources of noise and loss. But then around 8 or 9 years ago, there was sort of a stagnation where the last record for a planar transmon, for the lifetime of planar transmon was sort of set in 2012. So these have all been kind of pinned to around 100 microseconds since then. And this is despite really enormous efforts along these lines. And this is generally believed to be limited by dielectric loss in the qubits. There's also a lot of evidence that these losses are specifically related to surfaces. And this is something that we've talked about a lot in the context of the center. So for example, this is a beautiful data set that Chen Wang put together when he was in Rob Scholkoff's group a few years ago, where they plotted for many different devices with different surface participation ratios. You could see that there was just a scaling of the total quality factor. And the bulk losses set by all of the components should allow for Qs of something like 10 to the 9, but you can see that in general, it's sort of hard to break a Q of about 1 million. And you see this sort of clear scaling with surface participation ratio, both in this study and also in many other published data sets that show that these losses are likely related to surfaces or interfaces. So I thought I would just interject a small cautionary tale in interpreting a lot of data. So I just told you a story about studying surface spins in diamond. And again, these are spins that you can see when you apply some selective pi pulse, and then you can do spectroscopy on them. And that's how we know that they're sort of electronic spin a half G equals 2 defects, because you can just do spectroscopy and look at their Zeeman splitting. Because you can study these spectroscopically, this turned out to be kind of the main thing that a lot of people studied in the NV Center community for trying to improve surfaces. And indeed, if you look at, for example, Deer coupling rate versus T2, what you find is something that looks like a pretty good correlation that, maybe what's really ailing your T2 is that you have a really high Deer coupling rate, and then the surface spins are responsible for decoherence. But what we were able to establish through all of our careful sort of surface spectroscopy and preparation is that you actually can prepare surfaces where there is no correlation between the T2 change and the Deer coupling change. So what we found is that this apparent correlation between these two different parameters is actually a correlation of both the surface spin coupling and the T2 with depth. So our best hypothesis for the problems with shallow NV centers is not that they're dominated by these surface spins, but actually by other magnetic noise that you can't see when you try to selectively drive them. Okay, so with that aside, what we wanted to do was now look at superconducting qubits and try to figure out, by looking directly at the material systems, whether or not we can make any improvements. So just to orient you, this is sort of the typical qubit that the Hauck group fabricates. So you have an aluminum oxide component for the Josephson junction, and then the rest of the device is sort of made out of niobium. So the capacitor and the resonator are both made out of niobium. And then all of this is sitting on top of a sapphire substrate. So looking at this material system, we had two main hypotheses for the origins of this dielectric loss. The first is that you can just have contaminants at the substrate that lead to the surface-related dielectric loss. And then the second is something that Bob pointed out, which is that the oxides of niobium are actually quite complicated. You can get many different stoichiometries, and it's very hard to control. So this can lead to resistive loss, and is generally sort of just a bad insulator. So our stab at trying to improve both of these things was that first we tried to purify the substrate as much as possible through various preparation steps. What we found is that the as-received surfaces, even if you just looked at them with something simple like AFM, were kind of clearly highly contaminated. We can do standard sort of Parada and solvent cleaning to remove most of it, but then we can also do things like XPS to look for heteroatom contaminants at the surface. And what we found is that you can remove all of these heteroatom contaminants by just doing a selective, or by doing a gentle wet etch that removes the top few nanometers of material. And we can also go one step further and anneal the sapphire at high temperatures to recover atomic terraces. When we deposit tantalum on the sapphire substrates at high temperatures, you can get epitaxial-oriented growth of BCC phase tantalum with sort of 10 to 20 nanometer grains. It's sort of critical to characterize what exact type of tantalum you get, because if you just naively deposit tantalum in thin films, you tend to get the tetragonal phase, which has a much lower critical temperature. And what we found is that, as sort of predicted, the tantalum metal has a much better oxide, a much better behaved oxide than niobium does. So we can do sort of detailed XPS and TEM characterization of this oxide. And what we find is that the oxide is sort of always 2 to 3 nanometers and predominantly Ta205, regardless of what sort of processing we do. And it also appears to be very robust to differences in microstructure. So if you change the sputtering conditions of the underlying tantalum, we still get basically the same oxide. In collaboration with Ignace Yarrigue and Conan Weiland at NSLS2 in Brookhaven, we have started looking at these oxides in detail. So Ignace had this very nice work with Andrew Hauck's group from last year, where they looked at the oxides of niobium. And by doing variable photon XPS, they could do sort of depth profiling of many different stoichiometries. And you can see that, it's quite messy. You have lots of different stoichiometries, and then the suboxides can kind of penetrate fairly far below this interface. Whereas for tantalum, sort of to within the resolution of this technique, it looks like everything happens at the interface, and you have very, very little suboxide population. The last step is that, it's very important to actually have smooth edge morphologies in your final fabricated structures, because the important thing here is trying to minimize your surface participation ratio. And if you have sort of very sharp metallic structures, you can concentrate field at these rough spots and then get an apparent surface participation ratio that's much higher than your design surface participation ratio. So we had to work on our fabrication procedures to get sort of nice smooth edges as much as possible. Putting all of these things together, so purifying the substrate, replacing the metal with tantalum, and then working on our fabrication allowed for qubit lifetimes exceeding 300 microseconds. And what we're able to see is that with dynamical decoupling, the T2 gets up to around half a millisecond. It's also well known in this field that these T1s and T2s can kind of vary over time. So we were careful to plot a whole time series to show that we're really plotting the average T1s and T2s rather than just some cherry-picked data set. And we're really able to find to make these qubits with lifetimes exceeding 200 or 300 microseconds very robustly across many devices. Okay, so with the last 5 minutes or so, I thought I would talk about a little bit of preliminary data, trying to do more systematic studies of the loss of tantalum by doing measurements of resonators instead of qubits. So the idea is that we can do multiplexed experiments by making many resonators that are at slightly different resonance frequencies. And then because we're just making these out of tantalum, we sort of eliminate the variation in our aluminum oxide junction fabrication. And these resonators allow for a much larger temperature and power range, for interrogating microscopic sources of loss. They're also much more robust to processing. So, we don't have to worry about sort of the chemical compatibility of aluminum when we try to do hypothesis testing for improving Qs. So what we find is that if you look at the Q of these resonators as a function of power, we see that you get a better Q as you go to higher powers. And you see the saturation behavior, which is sort of consistent with a lot of reports of other qubits where you can see saturation of two-level systems. To try to understand what the likely sort of model is for loss, or to try to develop a model for losses in these systems, we can look at a full power and temperature dependence and very carefully fit our data. So this is now a temperature dependence from base temperature up to around 700 millikelvin for the same resonator. And then we can perform this at many different incident powers. And it turns out that we can fit this data very well, the entire sort of 2D waterfall plot, to a model that just incorporates two-level system loss, equilibrium quasi-particles, and then some sort of temperature independent Q other that limits everything up here. So there are a few kind of interesting sort of salient features of the data. So the first is that at very high temperatures, what we see is that all of these curves sort of collapse onto the same scaling. And this is just consistent with equilibrium quasi-particle loss. In this range here, we see that the Q actually increases slightly with increasing temperature. And this is consistent with a thermal population of two-level systems. And then the last kind of interesting regime is that at very low temperatures, we actually see this dramatic drop of the Q. And this actually, we believe, arises from the saturation parameter of TLSs changing with temperature. So in particular, if you just incorporate a model where the T2 of the TLSs goes linearly with temperature, then you can sort of fit this data very well to good agreement. Okay, and then to check that that this model makes sense, or at least that all of our data is consistent with this model, we can also look at things like the frequency shift of the resonator with as you do this temperature dependence. And we find that it's consistent, again, with a model where we have some two-level system frequency shift and some thermal quasi-particle based frequency shift. And then to check for consistency, what we can do is extract this parameter that is associated with two-level system loss. So it's basically Q TLS, which is basically the loss tangent due to TLSs to within a geometric factor from all of these different fits. So we can extract it from just looking at the power dependence, from this full temperature and power dependence, and then from this frequency shift. And what we find is that the QTLS knot is actually in pretty good agreement. Our power dependence sort of systematically overestimates the Q, but that these are sort of, the same to within a very small factor. And then now these are multiple resonators on the same chip where we get remarkably consistent results. So it looks like we really are extracting sort of a key material parameter. So now we can also look at all of these devices with different surface participation ratios and see where we are in terms of scaling with scaling of the losses with surface participation ratio. So this giant raft of points here is all of the data associated with that first paper that I talked about where we did tantalum qubits. So a lot of this is actually our fab development, and actually these two green points down here are niobium-based qubits. All of the gray points are extracted from that paper by Chen Wang that I talked about at the beginning. And then now these are resonators and qubits with different surface participation ratios. And you can see that there's some scatter in our fab, but we're really sort of systematically between these two different loss tangent curves at 0.75 times 10 to the minus 3 and 1.5 times 10 to the minus 3. So what we'd like to do is now use this as a basis for future improvements in qubits. Okay, so in conclusion, we had a really big leap in performance with a pretty simple material change. And I'll point out that somehow in this field, a very, very small number of superconductors have been fabricated into qubits and measured carefully. Largely because people were doing really beautiful science with the material systems that they have. But if I just go and write down kind of all of the fabricable, depositable metals that have reasonable TCs, it's a very tractable, it's a long but tractable list. So I think one of the lessons here is that there's lots of other material systems to explore, and and many possible qualitative leaps in performance out there. Our current devices are TLS limited, and now what we're trying to do is systematically study how various material properties affect this. We have a large number of ideas, and we now have sort of developed a little bit of a pipeline for having sort of rapid device feedback. And what we'd like to establish in this center is a number of rapid material proxies that correlate with these device measurements. All right, well, thank you for your attention. I'd like to thank or acknowledge all of the students and postdocs and collaborators who worked on these projects. So the NV Center work was led by P. Sanctoesen in my group and Bo Dwyer in Misha Lukin's group. And a lot of the the more recent surface spin work was actually kind of a nice story that when we all were stuck home last year in quarantine around March, we started fitting our data much more carefully and then started talking to the Lukin group and discovered that we could put together a very large data set of over 100 NV centers and really fit this carefully together. So we were working in collaboration with Bo and Tawana Urbach and Dolev Blufstein and a number of people in my group. The superconducting qubits work, the tantalum qubits paper was led by Leela Rogers in my group and Alex Place in Andrew's group. And the more recent resonator work has really been has been driven by Avik Dutta, a postdoc in my group. And then just this amazing team of just crackerjack undergrads, Trisha Madhavan and Huang Li and Yuqi Gang. who have really done incredible work. And as I mentioned, all of that work was done in collaboration, of course, with Andrew and also with Bob Kava's group in chemistry. And I'll stop here, and I'd be happy to take any questions.
Thanks very much, Nathalie. While people are contemplating their questions, I see there's also one in the chat. I wanted to just ask, in that picture I've seen several times now of, I don't know, it's some, is it an SEM picture with the side of the columnar looking growth of the tantalum? Mm-hmm. Should I be horrified by how columnar it is, or is that like what a film looks like? Or I know there are these instabilities that cause columnar growth, but I don't know what I'm looking at there. Is that good or bad or ugly or beautiful?
Yeah, okay, the short answer is that I am not sure what components of microstructure are important or not important. From the basic perspective of like, is this a good metal? It is a terrible metal because the residual resistance ratio is very small, and it's because it has all of these grain boundaries. But what I'll point out is that it is actually very nice that this columnar growth means that it's well-oriented and epitaxial, right? So you have this nice epitaxial growth right at the boundary. And the reason that you get these columns is because there's a threefold symmetry in the underlying sapphires. So there's nothing that picks a direction. So you can either have sort of 111 or 100 columns, and then they randomly nucleate. So one of the things that we're currently working on really actively is trying to change this microstructure and see what the impacts that has on resonators and qubits. You can sort of write down predictions that go in either direction. Like naively, you'd expect the grain boundaries to hurt because they house two-level systems or something. But then they might also help if they do things like trap quasi-particles. So
right.
I think
if there's somehow Josephson couple that saves you or something, yeah.
So my approach as kind of the dumb experimentalist is just, let's make a bunch of films with different microstructure and just measure what we get. And I think, we now have enough parameters that we can fit that maybe we can really learn something about what happens in these underlying films.
Okay, before I get to the raised hands, there's something in the chat from Mengen Wang. In the DEAR measurements, what acid is used that leads to carbon dangling bonds on the surface?
Yeah, so that's a really good question. So naively, you would not expect to have chemically stable carbon dangling bonds at the surface, because you would think that if you just make a dangling bond and you put it in anything, it should, get terminated somehow. So that was a big puzzle to us for a while. Adam Ghali has sort of developed an ab initio prediction that you can have these sort of protected dangling bonds at step edges. So that's our best guess right now. We just can't write down any other model, but you sort of get them really ubiquitously if you just do high temperature annealing and then acid cleaning, which is perchloric, nitric, and sulfuric. But you really just get them. There's no like special chemistry to get them. You just sort of get them every time you have a disordered surface.
Okay, and then one more from Chris Vandeval. SiO2 is a great passivating layer for silicon. It's lousy for, the analog is lousy for diamonds, and CO2 is a gas. Has there ever been a systematic investigation of heterostructures between wide bandgap insulators and diamond that could serve as a passivating layer?
Yeah, that's a good question. So in general, no. And the main reason is because there is no heteroepitaxial growth for diamond. So it's just such a weird, it's a very tiny lattice constant. So it doesn't really grow on anything and nothing grows on it.
Right.
And then the other kind of big issue is that naively, if you want to make a passivation layer, you sort of want the conduction band and the valence band to be around the conduction band and valence band of the material that you're trying to passivate. Doesn't necessarily have to be true, but that's kind of like the easiest sort of passivation to imagine. And diamond has this enormous band gap. and a very tiny electron affinity. So if you just kind of look at the band alignment with most stuff, it's sort of in the wrong place. But that being said, I do have an idea along these lines, Chris. So if you're interested, we should definitely chat.
I am very interested. Thank
Okay.
you.
Okay, let's go to the first raised hand, Rodrigo Cortinas.
Hello, thank you a lot for a nice talk. I had a question about the geometric interpretation of this dipolar sphere grown with time. I would have naively guessed that the expansion of that sphere was far too fast to explain the coherence at the scale of 10 microseconds. Could you maybe explain how it happens?
So sorry, let me just go back to this just so that other people know what we're talking about. Yeah, so the argument is that what we're trying to do is depict, how do I put this? What we're doing is depicting coherent coupling between your NV center and these surface spins. So the time is really, for a given surface spin position, how long does it take you to get, like a pi phase shift on this cosine decay curve?
I get it. Perfect.
Yeah.
Thanks. So the time scale is set by the coupling of these two spins.
Exactly.
And the distance, yeah.
And
sure.
and the coupling is set by the
It's a
distance.
strong function of the distance, yeah.
Got it.
Before I go to Peter Rakic, I'll just remind people we'll have a breakout rooms in a moment. Peter.
Yeah, excellent talk again, Natalie. So I just one simple question, or maybe not. In your TLS model, I'm just curious, did you have to deviate at all from the standard TLS that's used to describe glass? I'm just curious if you could make a comparison there.
Yeah. So I guess full disclosure, I completely expected to do these measurements and then discover that TLSs describe nothing because my I guess boot affiliation bias or something was that this entire field has been so focused on TLSs that can't possibly be the answer. But but what we did was so actually all of this modeling was sort of taken out of a thesis by Jiansong Gao, who's in an MKID group at Caltech, and I think their TLS model is almost 100% from the old glass literature. And then sort of the kind of key thing is that this T1, T2 temperature dependent stuff really relies on some assumptions about, I guess, like what's limiting your T2 essentially of the TLSs. So you have to put in some microscopic model that says that you have some spectral diffusion of the TLSs, and then this temperature dependence is just coming from like the bandwidth that you're interrogating at a given temperature.
Okay, yeah, thanks so much.